So we're going to talk about scales. In order to talk about scales, we have to talk about octaves. In order to talk about octaves, we have to talk about pitch. In order to talk about pitch, we have to talk about frequency. And in order to talk about frequency, we have to talk about sound. So let's start with the basic question. What is sound? Sound is vibrations in the air, right? Air molecules compress and then decompress, which is called rarefaction. And they do that really fast, and then it vibrates something in our ear, and that's how we hear sound. When we measure sound, we can talk about amplitude, which is how much the air molecules compress and decompress. And we can also talk about frequency, which is how fast they go back and forth. Pitch is related to frequency, but it's not the same thing as frequency. Pitch has to be perceived. Pitch is a perceptual phenomenon related to frequency. White noise, for example, has frequency, but it doesn't have pitch. We don't perceive pitch when we hear white noise. Similarly, when you play a note on a guitar, we perceive that as one pitch. But there's actually a lot of different frequencies going on in the sound. So for the purposes of talking about music, we can basically equate pitch with fundamental frequency of a sound. The other frequencies that are in there and their relative amplitudes, loudnesses, are what is responsible for musical timbre, or for timbre. It's not a musical thing, right? A guitar playing that note and a piano playing that note and a trumpet playing that note all sound different because of what other frequencies are going on, but they all have the same fundamental pitch.
Music.
Now, music is concerned less with the absolute frequency of specific pitches and more with the relationships among different pitches. Now, the first thing that anyone who studies frequency and pitch is going to notice is that when you double a pitch's frequency, it kind of sounds the same. For example, a pitch that is represented by the frequency 440 hertz, which means 440 compressions and rarefactions per second, we call A. Now, if we double 440 to 880, you get this sound. That is called an octave. There's something that sounds very similar between those two pitches. And we can go in the other direction as well. Half of 440 is 220. All of those pitches have a similar sound. So now if we say any integer multiple of a certain frequency is going to have a similar sound, we can get to the concept of pitch class. Pitch class is the collection of all pitches that are an octave apart, or a number of octaves away from some pitch. So the pitch class A involves this A, which is 440 hertz, and then all of the other A's that exist in the universe, which is basically 440 times n, where n is going to be either a fraction, a 1 over something, or an integer.
Scales.
Okay, so now we have the concept of pitch class. We know how it's related to frequency. What does this have to do with scale? Well, a scale is a collection of pitch classes. Because it's a collection of pitch classes, we can actually represent an entire scale by just looking at one octave long slice. Since they're pitch classes, the collection is going to look exactly the same as we go up to different octaves. Now, usually when we consider a scale, we put the pitch classes in order within an octave. So then you can perform the scale by singing or playing all of the pitch classes from a bottom note to the same note an octave higher. Here's an example of a scale from Indian classical music.
Sa ri ga ma pa da ni sa, sa ni da pa ma ga ri sa.
This scale contains 7 different pitch classes, which are here performed going up and down through the interval of an octave. Here's an example of an Arabic scale. Again, we've got 7 pitch classes through an octave. Finally, here's a European scale.